construction of Liebig measure on Rn. When we construct Liebig measure on Rn, I mean R cross n copies of R, it is usual to turn to Judel-Carathodry's procedure, which proves a positive measure from a given outer measure. But here we present an alternative approach based on the idea of extending the volume of n-dimensional intervals to wider classes of subsets of R. So, first definition. Let A equal to A1, A2, so on, An comes to Rn, and B equal to P1, P2, P3, so on, Bn belongs to Rn, such that Ai is less than Bi for all I. Okay, means A1 is less than B1, A2 less than B2. This is for all I. Then a set of the form all those x, x1, x2, xn comes to Rn. Ai is less than xi less than Bi for all I, or any set obtained by replacing any or all of the less than sign y less than equal to. I mean, we can place this y less than equal to, or we both have, we can place both less than y less than equal to is called an n cell. It's called an n cell. The volume of each n cell is defined to be volume of W product I from 1 to n Bi length of the intervals. Second definition, for any A, A1, A2, An element of Rn, and delta greater than 0, the set of the form Q A delta equal to all those x, x1, x2, so on to xn belongs to Rn. AI is less than xi, less than equal to xi, less than AI plus delta for all I. For all is called a delta box. It's called a delta box with center at, with corner at E. See, for example, in R, data box is this like this. This is AI. Take this origin, AI plus delta. Delta box. This is delta box in R. Okay, so R2. In R2 it will look like this. Say here A1 this is A1 plus delta. Here is A2. Say A2 plus delta. Extend this. This is A1, A2, delta, delta, delta. Okay. In R2. This is what we have here. A1 plus delta, A2 plus delta. So this is delta box. Okay. So this is how the delta box will look like in R2 here. Okay. Now define another set. Let's define another set for k belongs to n. Let Pk all those x, x1, x2, so on to xn in Rn such that xi is equal to Ri upon 2 power k. Ri belongs to Z for all I. Okay. Means integral multiples of 2 power k, 1 upon 2 power k. In other words, Pk is the set of all points x belongs to Rn whose coordinates are integral multiples of of 2 power minus k. Okay, each coordinate here is integral multiple of 2 power minus k. Okay, now we take collection of all these delta marks. Let omega k be the collection of all two power minus k boxes with corners at points of pk. That is what it means. That is omega k, all delta boxes a 2 power minus k such that a belongs to pk. This you have. Okay, so this collection, the collection omega k from 1 to infinity satisfies the following properties. Property A. For a fixed k, each x belongs to Rn lies in a unique member of omega k. Second property, if q dash belongs to omega k, dash belongs to omega k, omega r here, and r is less than k, then either omega dash is contained in omega double dash, or they are disjoint, or omega dash q dash intersection q double dash is empty. They are disjoint. If q also. So what you see, for a fixed k, each x belongs to Rn lies in a unique member of omega k. Okay, you can see from construction here. B, if omega dash belongs to, if q dash belongs to omega k, q double dash belongs to omega r, and r is less than k, then either q dash is contained q double dash or they are disjoint. C property it has, if q belongs to omega r, then volume will be 2 power minus Rn, n-dimensional. And if k is greater than r, then pk the set, then the set Pk has exactly 2 power k minus r n points in Q. After R, I mean the property, every non-empty set in Rn, every non-empty open set in Rn is a countable union of disjoint boxes belonging to omega 1 union omega 2 union so on. So these properties this omega, the collection omega k will have. Okay, so theorem 1.4. There exists a positive complete measure M defined on sigma algebra M in Rn with the following properties, First property is A. Measure of W is same as volume of W for every n cell W. P property. M contains all Borel sets in Rn. More precisely, this E belongs to sigma algebra M if and only if and only if there are sets A and B in Rn such that A is contained in E, is contained in V. A is an F sigma set, B is A G delta set, and measure of B minus A, this is 0. Also, M is regular. Okay. I mean inner regular as well as outer regular. Let F belongs to CC, Rn, and suppose F is real. Let W be an open N cell which contains the support of F. Since F is 0, because support of F is contained in W. So F is 0 outside. Since F is 0 outside the compact set, outside compact set, support F is uniformly continuous on Rn. Okay, since F is uniform to Rn, okay, since F is 0 outside compact, F is, we write here, F is uniformly continuous on Rn. Thus, for epsilon greater than 0, there exists an integer k naught and functions g and h with the following properties. Property 1. Support G is contained in W and support H is contained in W. Actually, you can see this property by theorem 4.19 of book Walter Woodin, Principles of Mathematical Analysis. Principles of Mathematical Analysis. These properties you can see from the theorem 4.19. Part second, G and H are constants on each box in the collection omega k naught Q of A 1 upon 2 power K naught. A belongs to Pk. Means GHR constant of this collection. Third property here, G is less than equal to F less than equal to H. And fourth property, H minus G is less than epsilon. So we check here. We also check that for any k greater than equal to k naught, lambda k naught G is same as lambda k G, and lambda k naught H is equal to lambda k H. This we'll check here. In fact, if k greater than k naught, then Pk has exactly 2 power k minus k naught. So we move k naught coordinates. This k minus k naught and points in Q of A 2 power minus k naught. Because as k becomes bigger, 1 by 2 k becomes smaller. This delta box becomes smaller. Okay. Since G is constant, on minus k naught, we have 2 power minus kn summation x belongs to Pk Gx is equal to 2 power minus kn two power k minus k naught n. Okay, Pk has this 2 power 2 minus point k minus k naught n points into C, where Gx equal to C on Q of A 2 power minus k naught. Because G and H are constants on each box. Okay, and this value becomes kn will cancel out. We are left with 2 power minus k naught n into C, and this value 2 power minus k naught n summation x belongs to Pk naught, okay, G of x. Why? Because there is only one point, because there is only one point of pk naught in q of a minus k naught. Okay, on where on okay, this is true. This is true on q of a 2 minus k naught. So with 2 power minus k naught n summation x plus pk naught gx on q of a 2 power minus k naught. Correct? So because it is only 1 point. Okay. Similarly, on other 2 power minus k naught boxes, we have the above equality. But this implies lambda kg is same as lambda k naught g. Similarly, lambda k h is same as lambda k naught h. Now, g is less than f less than h implies for k greater than k naught lambda k naught g is equal to lambda kg, and this is less than equal to lambda kf, and this is less than equal to lambda kh, and this value is equal to lambda k naught h. Put this equation, second equation. Okay, correct. Since h minus g is less than epsilon and support of h minus g is contained in W, it follows that lambda k h minus lambda k g is less than epsilon time volume of W. Okay, for k greater equal to k naught. Put this equation as 3. Okay, means up by lambda k naught. So this is less than volume epsilon time volume of W. Forget like this. So lambda k h minus lambda k g is less than epsilon volume, means you can this value from here we get x h minus g d mu here. This value less than epsilon, integral will be equal over volume, because outside h minus g less than, means this will be d mu means volume of the means we'll get here epsilon to volume of W. Okay, with integral over will be on W. So this is epsilon time volume of W. So here, okay, okay. Yes. As G is less than F less than H, thus the upper limit and lower limit of sequence lambda k f k tending from 1 to infinity differ by almost at most epsilon time volume of W. And as epsilon greater than 0 arbitrary and as epsilon greater than 0 was arbitrary, we see that this limit exists, limit k tending to infinity lambda k f, this limit exists. Question 4, exists for f belongs to CCR f real. Okay, Rn. Now suppose f belongs to CCRn, then f you can write as f1 plus eta f2, where f1 equal to real f and f2 equal to imaginary f. Define lambda as lambda f equal to lambda f1 plus lambda f2 eta. What we see here? It is complex number. So thus we see that lambda is from CCRn to C. Complex value is a positive linear functional. Thus, Rees representation theorem there exists a sigma algebra M in Rn and a complete measure Borel measure M on M such that integral Rn f dm 5. Now Rn is compact, sigma compact. Now Rn is not compact, it's sigma compact. Now, since Rn is sigma compact, the measure M is called, the measure M is regular, is a regular measure. We proved in theorem 1.3. The measure M is called, the Liebig measure is called the Liebig measure on Rn, while M is called the sigma algebra of Liebig measurable sets. Okay. Now the proof of part A, B, C, D, E. Students can refer to part A, B, C, D, and E. The students can refer to theorem 2.20. Theorem refer to theorem 2.20 of Walter Rudin. Real and complex analysis.